Right, good morning. So as you saw in Ryan's announcement, he's out this week, and you're going to have me. In case you forgot who I am, my name is Javier Peña. I'm a colleague of Ryan's. I work in the Tepper School. And if I get in trouble, luckily we still have some TAs here who can rescue me, okay? So today and Wednesday, I will tell you about Primal dual interior point methods. And I want to share just a personal anecdote. A couple of things. When I came to grad school many years ago, in the 90s, this subject was all the rage. So the opportunity to tell you about this is really kind of fun because it gave me this chance to go revisit this topic that is it is really, really nice. And something that happens in optimization, so this topic is not necessarily the most popular topic now, but something that has happened a number of times in optimization is that ideas come and go. So even though this is not the hottest topic at the moment, it is a good thing to have to learn because you never know how things are going to evolve moving forward. And there are very powerful properties of interior point methods that I'll try to tell you about today. So this is going to go in two parts. Today is part one. We are going to talk primarily about linear programming. And then on Wednesday, we'll talk about semi-definite programming. So just a recap, since it's been a while, right? Almost 2 weeks. So this is where Ryan ended last time. So he was talking about the barrier method. And what we are talking about today is very related to the barrier method. Essentially, the barrier method provides the foundation for what we are talking about today. So remember, the idea of the barrier method is we want to solve that problem, right? And you can think about the inequality constraints in some sense is what makes the problem difficult, right? So if we want to solve that problem, one idea is to deal with the inequality constraints via this barrier function. Okay, so a picture that we usually draw that goes with that is think about your feasible set as something that looks like this. So let's say this is your feasible set. And instead of enforcing the constraints directly, what we do for the inequality constraints is include that barrier term there, phi of x. And intuitively, you can think about phi of x as some kind of magnetic forces that are pushing you away from the boundary of that set. So if you look at the phi of x function, you see that when we approach the boundary of the feasible set, when any of the h values approaches 0, then that barrier function blows up. All right, and then what is the barrier method? So the idea is to solve a sequence of those problems. So for each particular value of t, there is going to be one minimizer of that problem. So when t is very small, if you want to think about the extreme case, if we pick t equal to 0, then all that we are going to do is just find the point here that is farthest away from the boundary. So this would be when t is equal to 0. And as t is larger and larger, then we give more weight to the objective function. And then this is going to trace something that looks like a path like this. Okay, so any point, a particular point here is what we have called x star of t, and that is the minimizer of that problem. Okay, t f of x plus the barrier function subject to ax equal to b. And then that suggests an algorithm, and that is we start with an initial value of t0, greater than 0, find the minimizer for this problem for that value, then increase t, and then find the minimizer for the new problem, and so on. So there is a story that a friend of mine once mentioned in a conference that I always find memorable. So think about interior point methods as the following, as an analog of the following kind of situation. Suppose that someone walks out of a street and then realizes when they walk out of the street that they have lost their wallet. Okay? And then the wallet, they know they lost it at the other end of the street, where maybe it's dark and it's very difficult to go all the way to the other end of the street and find the spot where you lost your wallet. However, you are here at this end of the street, and then you can slowly start tracing your footprints back, and eventually you will reach the end of the street where you lost your wallet. So if you do that carefully, you will be able to trace your footprints and eventually find the spot where you lost your wallet. So this is something somewhat similar. The point where you begin here is where you realize you lost your wallet, and then you trace the path. It's like tracing your footprints until you get to the point, the solution to your problem. All right, so that's the barrier method. So what are we going to do today? So today, we are going to look at the same idea in a bit more detail, and in particular, we're going to look at that in the context of linear programming. And so we'll talk about the central path, which is essentially the same object that Ryan spoke about last time. And we will describe, the main purpose of today's discussion is to describe a family of interior point methods that are called primal dual path-following interior point methods. So that's the main goal, okay? So let me start by recalling linear programming and linear programming duality. Okay, so remember, a linear programming standard form is that type of problem. So it's a convex optimization problem where we have a linear objective. We have a set of inequality constraints that are linear, and then we have some inequality. The variables are non-negative. Okay, and recall something that we mentioned a few weeks ago. In principle, any linear programming problem can be rewritten in that form. So you can replace your constraints, massage your constraints. You can always write it in this so-called standard form. And then there is a little technical assumption that we are going to make for the discussion today, for the algorithms that are going to that we will talk about today, and that is assume that the matrix A is full row rank. So if you think about what that means that you do not have any linear dependencies on the equations. If you did not have that condition, you can always remove any kind of linearly dependent constraint and then ensure that your matrix A is full row rank. Okay? So that's linear programming in standard form. Let me keep it here for a moment. Okay, so linear programming in standard form. And then we have the corresponding dual problem. So the dual of this problem, you can go through the steps of constructing the Lagrangian and doing the max min, and then the dual problem is that other linear programming problem. So what we had here as the constraints that defines the objective, and then the vector that defines the objective in the primal problem defines the constraints in the dual problem. We can write the dual problem those two ways, right? The first formulation doesn't include the slack variables, but for interior point methods, it's useful to have the slack variables explicitly there. So the second formulation has the slack variables. And then throughout the rest of our discussion today, this problem here, I'll refer to this as the primal problem. And then that guy there, that's going to be the dual. Okay? So whenever we talk primal, this will be this guy. Dual will be that guy. Now, the key, I guess the key property of linear programming duality, actually duality in general, is this weak duality theorem. And I want to write the proof of that because it's a very straightforward proof. So what does it say? If we have a point that is primal feasible, right? So primal feasible means feasible for the primal problem. A point that is dual feasible, then the objective for the dual is a lower bound on the objective for the primal, right? And the proof of that is really completely straightforward, and I want to write it down because we are going to rely on it later on. So the proof of the weak duality theorem is one line. So if we look at Cx minus By, okay, Cx minus By, So I'm assuming that we're assuming that X is primal feasible, Y is dual feasible, right? So C, because Y is dual feasible, C is equal to A transpose Y plus S. And then because X is dual feasible, B is equal to AX. Right? So I'm just using the feasibility. Again, here I have used dual feasibility, and here I have used primal feasibility. Okay? Now, if you expand that, then you see that you get a product X transpose A transpose Y that cancels, and all you have at the end of the day is S transpose X. Okay? Now, X, again, if it's feasible for the primal, has to be non-negative. S is feasible, Y and S are feasible for the dual. So then this has to be greater than or equal to 0. Right? So that's weak duality. And then we have, and this is a very, very special property of linear programming, we have this much stronger condition that is called strong duality. And that is, if the primal problem is feasible, then it is bounded if and only if the dual is feasible. And when that happens, the optimal values coincide. So what that means is that we have, you can think about this as the primal problem is here, right? So think about this as the primal problem. We are trying to minimize C of X. And then the dual problem is something like this. So this is the dual. And we are trying to maximize B. And then, interestingly, these two things exactly match. Okay. The primal and dual optimal values match. Okay. All right, so now we have this, if you think about the weak duality theorem and the strong duality theorem, then you can take this one little notch further. You realize that because of strong duality, the optimal solutions to the primal and dual problems are points that are feasible for both, and the objectives coincide. Okay? Now, for the objectives to coincide, this should be equal to 0, right? But both S and X are non-negative, so if the product is equal to 0, that means all of the components are equal to 0. So that's the optimality conditions for both the primal and dual problems. So X star and Y star, S star are respectively primal and dual optimal solutions if we have if all of those conditions hold. Okay? If you think about the first two conditions and the last one, all that is saying is just that you have primal and dual feasibility. And then the third condition is usually called complementarity. Okay? Now, if you think about the KKT conditions, in the particular case when the problem that you're looking at is a linear programming problem, the KKT conditions are exactly the same as this. So you can think about this as just a particular special version of the KKT conditions. So I want to tell you a little bit about where we are headed. So the two main types of algorithms for solving linear programming problems are the simplex method. I imagine many of you have heard or have learned the simplex method. And then the simplex method was the first algorithm that was developed for linear programming in the 40s, late 40s. Interior point methods were created in the 80s. And there is a key difference between how the two algorithms attempt to solve the optimality conditions. So the two algorithms are, you can think about both algorithms as a systematic procedure to try to solve those equations and those inequalities. The simplex method essentially maintains the first three conditions, but the iterates may violate the fourth condition. And then it systematically goes through different steps until it realizes that I can match the first three conditions and the last. When that happens, then it has found an optimal solution. Interior point methods do something that can be described as follows. They satisfy typically the first two conditions and the last one. And instead, they aim for eventually solving the complementarity condition. Okay? So there is that conceptual difference between simplex method and interior point methods. So let me tell you a little bit about a little bit of history related to these algorithms and to linear programming. And this is just a few highlights that reflect my personal biases. So Danzig in the 40s developed the simplex method, and it's really one of those remarkable algorithms that to this date is still the most popular method to solve linear programs. Now, in the 60s, these two guys, Klee and Minty, they showed a counterexample. They showed a really neat example that some of you may have seen. They showed that the cube, so if you think about the cube, in Rn, they showed that the cube can be distorted a little bit so that if you start here, the optimal solution may be here, but the simplex method may have to do all of this traveling. So the simplex method may have to go, each iteration of the simplex method has a neat kind of geometric interpretation. It goes through some of the vertices of the feasible region. The simplex method may need to perform as many as 2 to the n iterations to solve a linear program that has only n variables and 2n constraints. So in other words, the simplex method has a pretty bad worst-case complexity. Now, for many years, this was a very central problem in optimization. There were many attempts to develop pivoting rules for the simplex method that would get polynomial complexity. It is a subject that still some people are trying to crack now. But then there was an interesting couple of breakthroughs that were of completely different nature. In the late 70s, this was in the Soviet Union. Kashian, Nemirovsky, and Yudin, they're all Russians. And in the late 70s, Kashian wrote this very nice paper. It's a very short paper. It's only a few pages long, like 5 pages long, that showed the first polynomial time algorithm for linear programming. And it was based on the ellipsoid algorithm that was developed by Nemirovsky and Yudin. And this was actually pretty cool. It was a big deal. There was an article in the New York Times at the time that this was at the time of the Cold War. And then there was major concern that the Russians were really, really ahead of us. They had cracked this key problem in computational mathematics that was so relevant to military operations and so on. So this got a lot of press. Now, the ellipsoid algorithm of Kashian really didn't go anywhere beyond a theoretical interesting result. It's theoretically strong. It's a polynomial algorithm, but it's computationally weak. It doesn't work well computationally. The simplex method works a lot better. Then a few years later, in '84, Karl Markar, who I believe at the time was a graduate student, he developed the first interior point method for linear programming. And that time, the story was different because it was the first interior point method that was also polynomial time. And at the same time, it was competitive with the state-of-the-art versions of the simplex algorithm at the time. So that was really cool because it was this different algorithm that was theoretically and computationally superior to the simplex method, or at least computationally comparable to the simplex method. And then pretty much for the last 30 years, there has been this really interesting horse race between simplex methods and interior point methods. So both implementations of the simplex and implementations of interior point methods have gotten dramatically faster and more powerful in the last 30 years. And today, pretty much every state-of-the-art linear programming solver offers both types of algorithms. In certain cases, for certain kinds of problems, the simplex method may be more appropriate. For certain types of problems, interior point methods are more appropriate. And then one more historical note here. The best theoretical complexity known for linear programming is due to Renegard that gave a Newton-based interior point algorithm. So what we are going to discuss in the next half an hour or so is essentially a version of what Renegard did back in the late 80s. Okay? All right. So good. So let me go into the technical details. So what is this? How does the algorithm work and everything? And some of this, luckily, is going to be review of the barrier method. So that's good news because that is familiar territory. So if you think about our primal problem, right? So if you think about our primal problem, so our primal LP is mean Cx, Ax equal to B, x greater than or equal to 0. So then if we were to apply the barrier method, then we just do what Ryan told you to do last time. That is, take mean Cx and then subtract the a barrier function for the inequality constraints, right? So this is log xj, Ax equal to B. Okay. Now there's a little difference here. You can think about my tau here as 1 over t in Ryan's discussion. But other than that, it's essentially the same thing. Okay. Now the dual, we can think about doing the same thing to the dual. Okay. So we have here the dual. So the dual is max, right? A transpose y plus s equal to c, s greater than or equal to 0. So again, we can think about this as max b transpose y. Since I'm maximizing, then I have to flip the sign of my barrier function. So this is tau sum of log of sj, right? A transpose y plus s equal to c. All right. Now there is a neat fact that I actually want to sketch for you. The two problems are actually dual of each other, dual in the sense of Lagrangian duality. So let me observe that here because this is really very neat. If we take the dual of the first problem, okay? So the dual of the first problem, first we need to set up the Lagrangian, right? So L xy, this only has inequality constraints, right? So this is going to be the same objective. And then we take y transpose Ax minus, actually, let me write it down, B minus Ax, okay? B minus Ax, right. Let me see. Yeah, let me write it down like this, B minus Ax. All right? So that's the Lagrangian. And then the dual problem would be, the dual objective would be to max a mean, right, of the Lagrangian, right? Now, if you think about what this Lagrangian is, so L of xy, let me group the terms that have x. So this is going to be C minus A transpose y x, right? And then minus tau sum of log of xj and B transpose y, okay? All right, so what happens here? When I look at, so the dual objective is this function. Right? So what happens to this dual objective? So you can look at, I need to minimize over x, this expression here. Right? So what happens if C minus A transpose Y has one single negative component? What happens if this guy has one single negative or even zero component? What do you do to that component of x? Yeah, you push it to infinity. You crank it up to infinity, and then that blows up, or that, I guess, makes the dual objective be minus infinity. Okay? So the dual objective is only going to be finite. So this is going to be finite only if this guy is positive. Okay? So this guy is finite only if this guy that I'm going to call S is positive. Okay? Only if this happens. And when that happens, you can minimize this part here is very easy to minimize. Right? Because all you have is the product of, so I guess you get here, you get the sum of Sj, xj, and then you have tau, the sum of log xj. Right? And then you have B transpose Y. So if you need to minimize this, what should you set xj equal to minimize these two terms? So I need to minimize, I can minimize this component-wise, right? You have Sj, xj minus log of xj, right? So I have Sj, xj minus log of xj. Well, minus tau log of xj, right? So what should xj be equal to minimize that? Maybe I should make that here. So we need to minimize Sj, xj minus tau log of xj. If I need to minimize this over xj, what do I do? Okay, this is like a kindergarten a minimization problem, right? It's not a Carnegie Mellon machine learning convex optimization. This is, maybe preschool convex optimization, right? Say that again? Yes, exactly. So you differentiate, right? And then it's tau over Sj. Okay, so this is attained at xj equal to tau over Sj, right? So if you plug that here, you get that the minimum, the dual objective. The dual objective is, well, this is going to be tau n times, so this is n tau, right? And then you get tau sum of log of tau over Sj plus B transpose Y. Okay? And then you see from there that we get essentially the problem, the dual problem. So we get n tau. Here you get n tau log tau. And then B transpose Y plus tau sum of log of Sj. Okay, so the dual problem is essentially this problem, okay, except for this little constant here that for the purposes of the maximization is immaterial. Okay, so this is kind of neat. And then what is really even neater is that if you look at the optimality conditions for this problem, just let's say the KKT conditions, or alternatively the KKT conditions for the barrier of the dual problem, the KKT conditions look like that. Okay? And just for reference, let me put back, let me misplace that here. Let me put back the optimality conditions for the original problem. Right? So the optimality conditions for the original problem were here, right? So those were the optimality conditions for the original primal and dual problems. The optimality conditions for the barrier problems are here. So it's kind of like a distorted version of the optimality conditions for the primal and dual problems. The complementarity condition, xj, sj equal to 0, has been replaced by this condition, right? Xj, sj equal to tau. Now, for each value of tau, there is a solution to that problem. And then if we look at the collection of all the solutions, that is the central path. Okay? So I have a little pop quiz question for you. How many solutions are there to the, how many possible values for x tau are there? How many possible values for y tau, s tau are there? How many solutions do we have to this problem, to the barrier of the primal? And how many solutions could we have to the barrier of the dual problem? What happens to the objective that we are minimizing in each one of the two cases? Is there something peculiar about the objective there? Could there be more than one solution? Maybe I should phrase my question more explicitly. Let me phrase that then a little differently. Who can explain why there should be at most one solution? There are strict, I'm sorry, say that again? Oh, no, that's a nice try, but that's not why, okay? Let me tell you why. So strong duality doesn't have to do with it, because, for example, in linear programming, you have strong duality, and in linear programming, you could have multiple solutions. Okay? So it's not because of the strong duality. Yes? The fact that A is full rank, that has to do with the uniqueness of Y, but there is something a bit more maybe fundamental from the point of view of convex optimization, from convexity. Yes? Exactly. Exactly. The log, so for the primal problem, the objective is strictly convex. So then there could be only one. For the dual problem, the S part is strictly convex. So again, at least as far as the S component is concerned, there could be at most one solution. And because we have full rank, that implies that the Y component also has to be unique. Okay? All right, so the central path is uniquely defined, and it's a nice smooth curve. So there is a picture that goes with this, and it's a picture that is always nice to think about. So if we think about our, say, our primal problem like this, suppose that this guy here, suppose that that's x such that ax is equal to b and x is greater than or equal to 0. Okay, and my objective function is here. The central path is a nice smooth curve here. Okay, that is the central path. So that would be the set of points. I guess that would be the primal central path. Okay, so x of tau such that tau is greater than 0. And then you have a similar picture in the dual space for the other two components, y and s. Okay? Now, there is a really neat fact here. Let me look at my notes to make sure that I don't mess this up. Yes, so there is a neat fact here. That actually, let me say something else, and then I'll mention what the neat fact is. But again, the set of minimizers as tau is greater than 0, that's the central path. So the idea of path following interior point methods is very much in the same spirit as the barrier method. That is, we are going to have an initial value of, say, tau 0, and then we would have a point, this is going to be our point x0, that approximates this x of tau 0. Okay? Then we are going to decrease tau now. It's the opposite of what Ryan was doing. So instead of increasing t, we decrease tau. So we're going to make progress towards our optimal solution. So we take an x tau 1 that is going to be closer in the central path to the optimal solution. And then from x0, we are going to use x0 as a warm start to get to a point, let's say x1 here. And then we'll keep pushing tau closer to 0, and we'll keep generating new points x2, x3, and so on. So the idea here is, again, the xk's are going to be approximate solutions of points on the central path as tau goes to 0. So there are a few details that we want to make a bit more explicit. So the xk, and this is something that maybe, I'm not sure that Ryan discussed in that much detail, but for each value of tau k, we do not exactly solve the barrier problem. We do not get exactly x of tau. Instead, we get something that is close enough to x of tau. Then we decrease tau, and we move to the next point. So there are a couple of things here to clarify, and that is, what do we use as a measure of proximity to the central path? How do we decrease tau? And how do we update our iterates? And that is, those three are kind of the ingredients at the heart of primal dual interior point methods. So I need to introduce a little bit of notation to make everything more explicit. So there is this is kind of standard notation, F0. F stands for the feasible set, primal dual feasible set. So F0 is the set of points that are strictly feasible for the primal and dual problems. So we want the primal constraints to hold, the dual constraints to hold, but then X and S positive. Okay, so that is F0. Now there is a really neat fact. If you think about the following map, so if you think about this map, if you think about X, Y, S, and we think about X1, S1, up to Xn, Sn, this is incredibly cool. F0 is isomorphic to Rn++. So in particular, this mapping from F0 to Rn++ is a bijection. Okay? It is something really, really cool. I don't know, maybe Ryan will give you that as a homework, or one of the TAs here, or even if you don't get it as a homework, think about that. This is a bijection. It's a really cool fact. So that means you can think about the strictly feasible regions of the primal and dual problems kind of as if they were Rn++. Okay? Now, there is also this other piece of notation. When we have X and S in Rn, it's very standard when we talk about interior point methods for linear programming to write big X for the matrix that has in the diagonal X, and big S for the similar matrix that we build by just taking the diagonal of little s. So you can think about this product here. This is just big X, big S times vector 1. Okay. And there is this other piece of notation. Given x and s, non-negative, mu of xs is defined to be the average of the pointwise components of products of x and s. So another way of thinking about that is mu is x transpose s divided by n. Okay. So observe something here that is, completely straightforward, but this is something we're going to use. If x, y, and s is a strictly feasible point, then the gap between the primal and the dual is, do you remember, this is a calculation that we did a little bit earlier. Does anyone remember what that is? Let me refresh your memory. So when we do this calculation, we get S transpose X, right? So this is S transpose X. That is N times mu of X S. Okay? So the mu, in some sense, measures how far we are from optimality. If we take N times mu, that gives us what is the gap between the primal and dual. When that gap is small, that means that we are close to optimality. All right, so now remember the key points that we want to clarify here are what is the proximity to the central path, how do we decrease tau, and how do we update our iterates. So in some way, we need to formalize what it means to be near the central path. We want to formalize what it means to be near the central path. So this is the so-called two-norm neighborhood of the central path. So that set that we called N2 of theta is x, y, s, strictly feasible, such that when we make this product, x, s1, if we subtract mu 1, the two-norm of that is bounded in terms of mu. So there are two ways of envisioning what N2 of theta is. The easiest way, because it's much easier to draw pictures in Rn+, the easiest way is to think about so N2 of theta, that looks like this. If we think about it in this space, so these are all the components, say x1, s1, x2, s2, and so on. If we were on the central path, exactly on the central path, what happens to each one of these components, xi, si? If we are on the central path, the central path equations are these equations. What happens to each component xj, sj? Because the answer is here, right? If we are on the central path, then the components xj, sj, they're all the same, and they're equal to tau. Okay, so when we are on the central path, we are in this ray here. So this would be the central path. Okay, and again, I'm looking at this after we make this identification here. Now, if we are instead in this neighborhood, N2 would look something like this. It's like a little cone around the central path. So this would be, that set would be N2. Okay. Now, if we think in terms, so this is what happens if we think pictorially, if we identify our primal dual strictly feasible set with Rn++. It's very easy to visualize this. Now, if you think about undoing this, then the central path is here, and the neighborhood of the central path would look something like this. Okay, that would be N2 of theta in the primal space. So some kind of neighborhood of the central path. Okay. And remember, we needed to worry about the proximity to the central path. Also, how do we decrease tau, and how we update our iterates. So the central path is here. So again, I have a pop quiz question for you. What happens if tau, if theta is as small as you could possibly choose it, if it is 0, if theta is equal to 0, what happens to my neighborhood of the central path? What is n2 of theta if I pick theta equal to 0? It's the central path itself, because what would happen there is I would be forcing, I have no room there. I give myself no slack on what the different components of x, S1 should be. They should all be the same, right? They should all be equal to mu. So when theta is equal to 0, we would have exactly the central path. The bigger theta, the wider the central path, the wider the neighborhood of the central path. So that's n2 of theta. And then there is a similar so the n2 of theta is called the 2-norm neighborhood. And it's typically a very small neighborhood of the central path. N infinity, or more precisely, n minus infinity, is the neighborhood that I described below. So it's very similar. Again, if you think in terms of this picture, n infinity, instead of saying, of forcing to be in a small cone around this ray, I am allowing myself to get much closer to the edges, depending on how small gamma is. So if gamma is a tiny number, then n minus infinity would cover most of this space. So let me draw this in a different picture. So again, if we think about this is the central path, if we make that transformation, and then n infinity is something that is typically much bigger, all of that would be n minus infinity of gamma. Okay? So in particular, if we take gamma very close to 0, if gamma is a tiny number, n minus infinity of gamma is almost all of this. In other words, n minus infinity of gamma is almost all of f0. By contrast, n2 of theta, even if we pick theta equal to 1, n2 of theta is typically going to be a small neighborhood of the central path. It's going to be just a small cone around the central path. All right. So I think I have almost everything ready to describe the algorithm. Maybe there's only one more key ingredient here, and is the following. So the central path, again, are the points that are defined by those equations. Primal and dual feasibility, and the third equation there is some perturbed version of complementarity. And of course, x and s are greater than 0. So if we forget about the inequalities and we only think about the equations that we need to satisfy, we can think about solving those equations with Newton's method. So if you think about solving the system of equations with Newton's method, what you do to apply Newton's method is approximate the system of equations with a linear approximation. So the Newton step equations are the equations that are written there at the bottom of that slide. They are a linearization of the equations that we want to satisfy. Okay? Now, with that, I actually have everything to describe the first primal dual path following algorithm. So it's this remarkably short algorithm. You pick two constants, theta and delta, such that that inequality holds. So I guess to ensure the inequality that I need, that is theta squared plus delta squared divided by this less than or equal to 1 minus delta over square root of n times theta, we can choose, for example, theta equal to delta equal to 0.4. Okay? And it's clear that if both delta and theta are small enough, then this is going to hold. So, for example, 0.4 will suffice. So how does the algorithm proceed? We begin with a point in that neighborhood of the central path. And then what we do at each step is chase a point with a particular value of tau. The tau that we pick is mu times this factor. And then we apply Newton's step with this initial point, with the previous iterate, and with that value of tau. And then we update the next iterate is the previous iterate plus the Newton step. Okay? So if you think about it, say, in the picture here, a particular value here would be for some value of tau. So what that algorithm does is it takes a point here. This is my xk, yk, sk. And then the mu of that point would be somewhere around here. We decrease that mu, that would be the tau, and then we try to chase this point, and that would be our next xk plus 1, yk plus 1, sk plus 1. And then we decrease again tau and keep doing the same thing. So that is called a short step path following algorithm. And the key theorem is the following. So if we do this, and this is what seems like magic, if you think about what we are doing at each step, we are just applying one iteration of Newton's method. We compute one Newton step, and that one single Newton step is what we use to generate the next iterate. There is no business here of outer and inner iterations as in the barrier method. We just apply one Newton step. We decrease tau, and we apply one Newton step. And then what is absolutely remarkable is that will ensure that we stay in the neighborhood of the central path. And it will also ensure that mu is decreased by that factor, 1 minus delta over square root of n. Okay? So let me tell you a couple of things about how this follows. I will not give you the full proof because the proof has some technicalities that I'm not going to have time to get into. I would love to, but we don't have enough time for that. But I do want to give you some idea of how the proof goes. Okay, some idea. So here is the Newton step, right? Here is the Newton step. So if you think about the Newton step, we have, so if we use the Newton step, let's look at x. I'm going to call x plus. This is going to be, just for shorthand, I'm going to call x plus. This is going to be xk plus 1. Y plus is yk plus 1. And s is going to be sk plus 1. So I don't have to write so many k's. Okay? And xk is going to be x, and so on. Okay? So if you think about so I want to give you an idea of how those two main conclusions of the theorem follow. So if you think about the first conclusion, what do we need to prove to ensure that each iterate stays in the neighborhood? What does it mean to be in that neighborhood? What would we need to prove? Let me put the definition here of the neighborhood. Maybe that would help. So if this was to appear in your exam, right? You have the definition of what the two neighborhood is. You have the definition of the algorithm. And first question in the exam is, prove that the algorithm generates iterates that stay in that neighborhood. How would you go about proving that? So somehow we need to prove that the point stays here, right? And the algorithm generates each new point by updating the previous point. So we start with an initial point that is in the neighborhood. What we would need to do is inductively show that every update maintains that property, that stays in the neighborhood. So to be in the neighborhood, then these equations would have to hold, right? And these components will have to remain positive, and this has to hold. So now, if you think about the Newton step, the Newton step is this. The Newton step is we solve these equations, right? So if you think about what happens to x plus, so x plus is x plus delta x, y plus is y plus delta y, and s plus is s plus delta s. So what happens to ax plus? So ax plus is ax plus a delta x. Now, the previous iterate, what was ax equal to? If my previous iterate is in the neighborhood, what happens to ax? Is b, right? So this guy is already b. And what happens to a delta x? What is a delta x equal to? So my delta x, delta y, delta s are the solution to this, the Newton step equation. So what is a delta x equal to? 0. So this is just, so this checks out, right? Now, likewise, a transpose y plus s plus, this is a transpose y plus s plus a transpose delta y plus delta s. So again, this guy is c, and these two guys are the first equation here, so that's 0. So again, this is equal to c, that checks out. Now the difficult part is to show that x plus and s plus are positive, and to show that this inequality holds for the new point. So let me tell you one part of how this follows. I don't have time to tell you everything, but if you look at x plus s plus, so if we wanted to compute, to check that we are in the neighborhood, we will have to compute this and subtract mu of x plus s plus 1. Okay. So let me at least show part of this. This is, what is this equal to? X plus s plus 1. So this is x plus delta x, s plus delta s times 1. So if you think about what this ends up giving you, once you unravel that, you get x delta s, and then s delta x, and then you get delta x delta s 1. Oh, and I forgot, I guess, x s. Okay. So now, or maybe I should be more explicit here, xs1. Now, take a moment to look at this last equation here. The last equation in the Newton step. So what does that equation tell me, this last equation? If I take s delta x and x delta s, what is that equal to? That's exactly what I have here, right? So s delta x and x delta s. So since the Newton step solves those equations, this part here is tau 1 minus XS1 minus. So this part is equal to that, and then we have delta X, delta S1, and XS1. So this guy cancels, and we get tau 1 plus delta X, delta S1. Okay? So the next, the new point that the new iterate satisfies this. If I wanted to show that this is near the central path, I will have to subtract some multiple of 1 and show that that's small. That basically has to do with showing that these guys, all of these products are small. But there is one small thing that I can show here. If I want to compute x, mu of x plus s plus, this is by definition 1 over n x plus transpose s plus, right? So if you look at this equation, what is x plus transpose s plus? Oh, I should show that here. What is this product equal to? So this is x plus s plus component-wise. If I want the sum of all of those, is the sum of all these components. Okay? So this is 1 over n. I have tau times 1, so this is n tau. And then I have delta s, delta x, delta s1. So I get delta x transpose delta s. Okay? So if you think about it, you get that mu of x plus s plus is tau, and then 1 over n delta x transpose delta s. Now tau, by the way that the algorithm is designed, tau is 1 minus delta over square root of n times mu of xs. And then I have this other component here that is x, delta x transpose delta s. Okay, so I almost get what I want. I almost get what I want. I want to show that the mu is decreased by that factor. I almost get what I want. To show that I actually get that decrease in mu, I would have to show that this is equal to 0, right? So now let me again look at the Newton step one more time. So if you look at the Newton step equations, observe that. So if we look at the Newton step equations, we have that A transpose delta y plus delta s is equal to 0. And we also have that A delta x is equal to 0. So if I multiply by delta x at the top, I get that delta x transpose A transpose delta s, delta y plus delta x delta s is equal to 0, right? Now, what is this first term equal to? Delta x transpose A transpose is just the transpose of this, so this is equal to 0, right? So this guy is equal to 0. So this shows at least some part of the theorem that shows that the mu decreases by this factor, okay? And I know there's many technical steps here, but this is kind of the key, that the mu decreases by this factor, okay? So I want to show you one very powerful corollary of this. If we know that the mu decreases by this factor at each iteration, the corollary is that if I want to get a primal and dual solution that has gap epsilon, it suffices to perform a number of iterations that is like square root of n log of 1 over epsilon. Okay? And let me show you how that goes. I think I have just enough time to show you that. This is easy. Once we have the second statement of the theorem, this is easy because after k iterations, what is mu of xk sk? If I want to relate that to mu of x0 s0, what is this equal to? What should I write here? If my mu decreases by a factor of 1 minus delta over square root of n at each step, then what is it after k steps? So this is 1 minus delta over square root of n to the k, right? So it decreases linearly. So then if you play around with taking logs, the corollary immediately follows. Okay? So from here, it follows that in O of square root of n log of n mu of x0 s0 over epsilon, we get xk, yk, sk, such that that this is less than epsilon. Okay. All right. So to be, I know this is late, but to stick to Ryan's practice, let's take a very short break here. Let's take a breather, and then when we come back, I'll show you two variations of this that are cool, and they will take just a couple of minutes, but I think they're nice. So let's take a very short 3-minute break. Stretch, breathe. All right, so this is the main algorithm that I'm going to discuss in detail, the one that we just finished. There are many variations on this same template. In particular, the reason that this is called short step is because that neighborhood, the 2 neighborhood, is a tiny neighborhood. So the steps that the algorithm would take are really short. If instead of the 2 neighborhood, we use the one-sided infinity neighborhood, the steps can be much bigger. So that would be the difference between trying to stay in a tiny neighborhood like this or being allowed to stay in a much bigger neighborhood. So because of that reason, this is called short step. This is long step. Okay? And the idea is very similar. The long step algorithm, the idea is very similar, but we use a wider neighborhood. There is a small difference here, and is that now we may need to do some line search. We may need to do some line search to stay in the neighborhood. Okay? That is something that is theoretically very powerful about the short step. In the short step, we take exactly a unit length Newton step. By contrast, in the long step, we have to do some kind of line search here to stay in the neighborhood. And then the theorem is very similar. The iterates are guaranteed to stay in the neighborhood, and the mu is guaranteed to decrease. Now, if you compare this to the previous result, which one of the 2 algorithms would theoretically be faster? The short step or the long step? Which one would decrease the gap faster? The short step algorithm or the long step algorithm? Which of these 2 factors is we want to decrease, right? So we want the factor that is closer to 0. So which factor is smaller, this factor or that factor there? Oh, let's ignore, let's suppose that delta are the same things, okay? Let's suppose that delta are the same. So the dominant part here is really n, because we're thinking about, big problems. So it's really not, the delta is just a constant. So think about that as some big O constant. So suppose that the delta are the same. Which one of these would you prefer? Delta over 1 minus delta over square root of n, or 1 minus delta over n? But this one would be a much smaller number, okay? In particular, if you think about the corollary, this would mean that after something that is roughly like square root of n log of 1 over epsilon, you get an epsilon solution, whereas here is n times log of 1 over epsilon, okay? Now, this is kind of a paradox of interior point methods. The short step algorithms are the ones that are theoretically the fastest, but in practice, they're extremely slow. Long step methods theoretically are weaker, but in practice work better. Now, in practice, you don't even implement that long step algorithm, because the long step algorithm requires that we begin with an initial point that is in the neighborhood. In practice, we don't even implement, in practice, the only thing that we maintain is that x and s are positive. And then in practice, what you need to do is actually aim for solving all of the equations, the primal equations, the dual equations, and the complementarity. So there is another theorem, another algorithm that would do that. And then there is another theorem that guarantees that that algorithm would eventually get you a solution. But the conclusion of this theorem is weaker than any of the previous two. So you realize it's kind of an interesting paradox. This is theoretically the fastest one, but what we can actually use to crunch numbers and produce solutions faster is something that theoretically is much weaker than this. And then just to show you that, this is the last thing that I want to show today. This is really cool. Let me show you an algorithm here in MATLAB. This is something that I got from a colleague in Rice, Ying Zhan. There's nothing fancy about that MATLAB code. I wrote it, so it cannot be that fancy, okay? It's very straightforward. All we are doing there is solving, the main operation here is solving the Newton equation. And then I generate some random instances of size, say 500 by 1,000. Okay, and I just take care of generating them so that they're feasible. And then if we solve this, this finds a solution in at most 30 iterations, okay? So I generate a new instance, and again, this solves that in about 30 iterations. Now, what I have implemented there is something that is very similar. It's very similar to this last algorithm here. It's something very similar to that last algorithm, except it's a little more sloppy than that last algorithm. It doesn't even worry about staying. The only thing that it worries about is making sure that my x and s variables stay positive. Other than that, it just takes the Newton step at each step, and it doesn't even bother to check that this condition holds. If we wanted to be theoretically a little more sound, we could include an extra line in the algorithm that does some backtracking to do the line search to ensure that both of these conditions hold. But even without that, something that is remarkable about interior point methods is that in practice, they work actually a lot faster than what in theory they're predicted to work. All right, so I think maybe the last thing that I want to say here is, so again, this is a version of the algorithm that would be for infeasible, that doesn't maintain feasibility. So the initial points here, all that we ask about the initial points is that they be, the x and s be positive. And again, the key step here at each iteration is to compute the Newton step, where the Newton step now is going to be a little more complicated because we have to worry about the primal and dual equations. So RC and RB would be the residual in the primal and dual. Other than that, is the same kind of principle. And you could take the conclusion or the property of this algorithm is that mu converges to 0 linearly. However, the constant is not as nice as the constants that we had here or in the long step. And consequently, the residuals also converge to 0. Now, you could take this even a little bit farther. You can look at any kind of convex optimization problem. Then you look at the KKT conditions. The KKT conditions are here. Then you look at the central path. The central path is there. The Newton step would be the solution to this. And the algorithm that I just described for you also extends now to more general convex optimization. So this would work similarly. You could, again, write a piece of code that has just a few lines that does this. And I guess the part to be careful about here is find the step length after you solve the Newton step. Find the step length that guarantees that the constraints are satisfied and that the residuals are reduced. So with that, I'm going to close this chapter today. On Wednesday, what I will tell you about is how we can take very similar ideas to semi-definite programming. And then it's the same idea, proximity to the central path, Newton step, and a primal dual scheme. So we'll talk about that on Wednesday. If you're interested in some references, a lot of what I have discussed here is based on this very fine reference for primal dual methods for linear programming. Okay, it's essentially all of what I discussed today is from there. Okay, so I'll see you on Wednesday.